Okay, let's talk a little bit about formally what we have on our postulates, definitions, and propositions for unified geometry about triangles. Now remember, this builds on our incidence stuff that we have from the first week here, first couple of weeks, then our things that we did on distance and order, our information on angles and convexity here, and we're building on that to talk about triangles. Now, the first thing I want you to notice is there are definitions. We have lots of definitions in geometry. There are lots of definitions in mathematics in general, but geometry has probably more than its share. And it's very, very important when you're studying mathematics that you memorize the definitions. So one of the things that you want to do is make yourself a list of, I'd say make yourself out some flashcards. On the one side, write the term that we're defining, and on the other side write the definition, and do it from what we have here in this list of postulates, definitions, and propositions, and write down the definitions as they are here, and then you just need to memorize them pretty much word for word, because often if you change some words, then you change the meaning of the definition. And certainly these are good quiz questions, as you have noticed, and these should be easy questions for you to just knock out the definitions, but you do have to practice it to be able to do that. And of course, the flashcard idea, I think, is an excellent way to go at that. And of course, you also learn these things by using them in your constructions, proofs, and investigations. So let's just go through some of this very quickly. So given any three non-collinear points A, B, and C, we define triangle ABC as the union of the line segments AB, BC, and CA. So notice that is the definition of a triangle. In that definition, with the points A, B, and C are called the vertices of the triangle ABC, or one of them is called a vertex of that triangle. The angles ABC, BCA, and CBA, which actually are made up of rays, are the interior angles. The interior of a triangle is the intersection of the interiors of the interior angles of the triangle, and the exterior of a triangle is the part that's not in the interior of the triangle itself. An exterior angle of a triangle is an angle that forms a linear pair with one of the interior angles, and then you have remote interior angles. So we have an angle up here that's an exterior angle, and the angles here at A and C would be remote interiors. We're going to call the longest side of a triangle the hypotenuse. Some people reserve that for the side opposite a right angle. We're going to say it's going to be the longest side period in any triangle. Then we can classify by sides and angles. Scalene triangle. A triangle is a scalene triangle if and only if it has no two sides that are congruent, so they're all different lengths. A triangle is isosceles if and only if it has at least two congruent sides. Could be all three congruent to each other, but at least two congruent to each other. And a triangle is equilateral if and only if it has all three sides congruent. Notice these say nothing about the angles. We may be able to conclude something about the angles in certain geometries, and maybe not. But we have to just define these this way. A triangle is an acute triangle if and only if all of its interior angles are acute angles. It's a right triangle if it contains a right interior angle. It's obtuse triangle if it contains an obtuse interior angle. And it's an equiangular triangle if and only if all three of its interior angles are congruent to each other. And so we clearly have that. Now, the way we define this does allow the possibility, perhaps, in spherical geometry, where you could have something that has both a right and an obtuse angle in the triangle, in which case it would be both a right triangle and an obtuse triangle. A regular triangle is both equiangular and equilateral. In a right triangle, the sides that are included in the right angle are called legs, or that form the right angle, are called legs. In an isosceles triangle, the angle formed by the congruent side is the apex angles. The other two are called base angles. The two congruent sides are called legs. The other side is called a base. The distance between two geometric figures in general is the minimum of all the distance between any pairs of points when one point is on each figure. So if I want to find, for example, the distance between this point and this line, then I'm looking for the minimum of the lengths of all these possible line segments here and whichever one of those is the shortest, then the length of that will be the distance between that point and that line. Okay, so now we have some theorems, and some of these are assigned for homework problems. Prove these in some of the videos that we do that I'm going to post, okay? Especially some of the harder proofs. So then we talk about, each triangle is contained in exactly one plane. If two triangles are equal, meaning the same triangle, but they're named by different things, then the set of vertices has to be the same. It only has 3 vertices, basically. The interior of any triangle is a convex set. This proposition 39 is related to the theorem of Posh. And then we talk about triangle congruence, which I've talked about before, and these different properties. Okay. One note here. In the notation above, be sure that these measurements go around in order of the figure. You can go around clockwise or counterclockwise, but it's important to notice that corresponding parts have to have congruent measures in these criteria. For example, notice that in Euclidean geometry, it turns out that an 8, 12, 18 triangle and a 12, 18, 27 triangle have 3 pairs of corresponding angles congruent, and they also have 2 pair of sides congruent, the 12 and the 18. But the 12 and the 18 don't correspond if you make the angles correspond, or if you make the sides correspond, then the congruent angles don't correspond. So these 2 triangles do not satisfy, well, they satisfy the angle condition, but they do not satisfy any of the others because the corresponding parts aren't matching up. Alright, now let's get into the new stuff here. Everything above this red line is going to work in Euclidean, taxicab, hyperbolic, and spherical geometries. But one of the things that we found in our investigations is that none of these congruence criteria here are going to work in taxicab geometry. So that's one thing that taxicab geometry has that's very different than the others. And so if we're going to force these things to some of these to give us congruent triangles like they do in Euclidean geometry, and we're going to sort of work our way towards Euclidean geometry, we need another postulate. And so we choose the one, side angle side postulate. We choose that one because, if you remember, we can choose any 2 lengths and any angle measurements, proper angle measurement, and 2 positive lengths, and they will always generate one triangle and only one triangle, or at least only one congruence class of triangles. So we're going to accept that one as the postulate. Now I'm going to state this 3 different ways. First of all, I want to say, if I've already defined the Sas condition as I did up here, then the easiest way to say it is this. If a pair of triangles have the Sas condition, then they are congruent. If we want to spell it all out in words, we could say it this way. Given a correspondence between 2 triangles, or between a triangle and itself, if 2 sides in the included angle of one triangle are congruent to the corresponding parts of the second triangle, then the correspondence is a congruence. Or, if we can specify that out by naming things, probably the most explicit way we could do it is this. If we were given triangle ABC and triangle DEF, with line segment AB congruent to line segment DE, angle ABC is congruent to angle DEF, and line segment BC is congruent to line segment EF, then triangle ABC is congruent to triangle DEF. So that's a postulate. We accept that without proof, so we don't have to prove that. In fact, we cannot prove that. And notice the existence of taxicab geometry shows that the Sas postulate is independent of the other 12 postulates that we have listed before this. So that's really probably the main reason why we wanted to study taxicab geometry, is not only does it give us a nice cool geometry to look at, it gives us a little bit of a way to talk about a distance metric, but it also shows that this Sas postulate must actually be a postulate. It is independent of the others. So that's one of the main reasons why we study that. Now, then we can start with some congruence theorems. So Now remember, these from this stuff from the SAS postulate down, these things no longer apply, or at least may not apply, in taxicab. And certainly taxicab geometry, the ASA triangle congruence theorem, does not hold, and you've looked at counterexamples already. So basically I've said that three ways here, but if two triangles have the ASA condition, then they are congruent. And from that we can prove, between the SAS postulate and the ASA congruence theorem, we can prove the triangle's isosceles if and only if it has a pair of congruent base angles. And so this proposition 40 is going to work for Euclidean geometry, hyperbolic geometry, and spherical geometry, as is the SAS postulate. Now we get the side-side-side triangle congruence theorem as well. If two triangles have the side-side-side condition in all three of those geometries I just mentioned, then they have to be congruent. We can define a perpendicular bisector of a line segment to be a line which is both a bisector of the line segment and is perpendicular to that line segment. So I'll draw the Euclidean example. It's got to go through the midpoint if it's going to bisect, and it also has to be the unique perpendicular. We know there's a unique perpendicular there. We proved that earlier. Unique perpendicular to that line containing the line segment through that point. And there's only one of these things, so it's a unique object there, and so that gives us that. Now, one of the things that we want to show is that these two distances here are the same length. So if we take any point on the perpendicular bisector, it's the same length, same distance from both points here. So the points which are equidistant from a given point, C, A, and B, okay, and this point here, well, how about X? And we'll call this point M for midpoint. Okay, and any point here is going to be the same distance from both A and B. And this is, you can do the same construction in spherical geometry and in hyperbolic geometry. I'll leave those for exercises as you're investigating that theorem. Given a line and a point non-aligned, there exists at least one line through P that's perpendicular to the line. So given a line here, and we said earlier that if we had a line, let's just make a line here, and a point on the line, there's exactly one perpendicular. But this says if we're given the line and a point P that's not on the line, so this is our line L, and this is our point P that's not on the line, okay, that we can select those two things, and since there's only one perpendicular, we should be able to go to here and construct the perpendicular line there. Let's see, I need a point there first, won't I? Okay, and so that's a right angle. It doesn't matter where that point is, not on the line, over here. There's a unique perpendicular there. Okay? No, I'm sorry. It says there's at least one perpendicular there. That's part A. Now, if the distance metric is unbounded, so that's going to be hyperbolic and Euclidean geometry, then this perpendicular is unique. There is exactly one. But if it's spherical geometry, it'll be okay as long as the point is close enough to the line. So if the point is within the bound, well, let's use pi for our bound like we've normally been doing. So if the point is if this distance to the line is less than pi over 2, then there will be a unique one. But if it equals the distance, the maximum distance you can get from a point in a line is pi over 2, and if that distance is pi over 2, then there's actually infinitely many perpendiculars. So you can think about that a little bit when you're working with that with your sphere. We'll examine that in class a little bit too. This next one, I'll let you read over that, but it's related to spherical geometry because it's talking about distance metric is bounded. So this one doesn't apply really to Euclidean or hyperbolic. But it says if the distance is, well, remember u is pi. So if the distance is pi over 2 from P to Q, and Q is on a line L, so this is like this point right here is our Q. And of course the lines don't look just like this. And Euclidean and spherical geometry, but if you had a line here and a point, and this distance is pi over 2, then what this is saying, then for every point on the line, the distance from P to that point is pi over 2, and those line segments, they all make perpendiculars. And so in an isosceles triangles, the legs each have length pi over 2, if and only if the base angles are both right angles. And in a pi over 2 spherical unit, pi over 2 radian, pi over 2 triangle has 3 right angles and 3 sides of length pi over 2. So you can look at that. Exterior angle inequality says we have the measure of an exterior angle is greater than the measure of either its remote angles, interior angles. That's true if for the distance metrics unbounded, so hyperbolic and hyperbolic and Euclidean geometry, that's true. It's sometimes true in spherical geometry. It's if the triangle is small, in the sense that all the sides are less than pi over 2, then the measure of an exterior angle of a triangle is greater than the measure of each of its remote interior angles. But this is not true if you have some triangles of size, if the sides are pi over 2 in length, or maybe greater. It could give us some problems. And so this one, you're going to be able to help use 46 to prove 47, and 47 is going to end up saying that the measure any two interior angles of a triangle, the sum of them is less than pi, and there have to be at least 2 acute interior angles. And that's also true in the spherical case if the triangle again has sides of less than pi over 2 in length. But if the sides get bigger than that, then that fails. Okay, and I'm going to just kind of start skimming over this real quickly. Triangle inequality, we've talked about that before. That's still going to hold in all 3 of these geometries. Scalene inequality says the largest side is opposite the largest angle, and vice versa. If the distance metric is unbounded, then one of the angles is right or obtuse, then the other 2 have to be acute, but not true in spherical geometry. And here's some things that we can do about right triangles in spherical geometry. Okay, and if you notice it, a lot of these have to do with the size of things. If the size of the triangles is small, it operates kind of similar to Euclidean geometry, but when the triangles get bigger, particularly when they get up to side length of pi over 2 from one side, some interesting things start happening. Okay, the Hinge theorem, or side angle side inequality, said if we have 2 triangles ABC and DEF, and AB and DE are congruent, then AC is greater than DF, that distance, if and only if the measure of angle B is larger than the measure of angle E. Now we get to the angle side triangle congruence theorem, and if the distance metric is unbounded, or if it's bounded and all the lengths of the sides are less than pi over 2, remember u is our upper bound, which is going to be pi for us, then the angle side condition is enough to make the triangles congruent. So angle side works for hyperbolic, it works for Euclidean, does not work for spherical in general, but if we have an additional condition that the sides are not too big, then it does work in spherical. Side-side angle theorem, of course, is not enough to, side-side angle by itself is not enough to guarantee congruence in any of those three geometries. We have the ambiguous case sometimes, okay? But either one of two things happens. If we have ABC triangle and triangle DEF with AB congruent to DE, segment BC congruent to segment EF, and angle C congruent to angle F, that's the side-side angle condition, then either the triangles are congruent, or if they're not congruent, basically the angles at A and D are either congruent and the two triangles are congruent, or if the angles are not congruent, those two angles are supplementary. We have some special cases. The big S, little s-A triangle congruence theorem. By the way, let me back up. Part A then is going to say you're either going to have, if I specify some measurements, you're either going to have no triangles possible, one congruence class, or two congruence classes. B, the big S, little sa theorem says if in addition to the SSA theorem condition, we also know that side AB is actually larger than side BC. The first S is larger, the one that's opposite the angles that are congruent. If we know that that's larger than the adjacent side, then that's enough to say that the two triangles are congruent. We can also do this if we know for sure that measure of angle A is greater than both the measure of angle B and the measure of angle C. That's enough to make the two triangles congruent along with the SSA condition. Okay? But it's not enough necessarily just that measure of angle A is a right angle or an obtuse angle. That is enough if it's in the unbounded metric. So that would be, for example, the hypotenuse leg theorem in the right triangle case, or if it's an obtuse angle, same thing. That boils down to the same thing, because if we know one's a right angle or an obtuse angle, it's definitely bigger than the other two in Euclidean and hyperbolic geometry, but not necessarily that's not necessarily true in spherical geometry. Okay. And the angle bisector theorem says if we take an angle here, I'll do an Euclidean example, and there's going to be an angle bisector that we can construct here. And if we take any point on this and we find its distance to this line here, which is the shortest distance, which is a perpendicular distance, so we're going to that point, and the distance here, which is also the shortest distance, which is a perpendicular distance. Okay, I'll hide that. And we're doing these two lines, this one and this one, and our claim is that those two have to be the same. And it doesn't matter where we go here, those are the same distance. And the shortest distance is a perpendicular distance here, at least in the case of Euclidean geometry and hyperbolic geometry. This is going to work. So you're going to have to investigate that a little bit more in the other geometries too. So here we have some more definitions. These are based on given a triangle ABC. We talk about a sevien, a median, an altitude, the height of a triangle, the incenter, the inscribed circle, circumscribed circle, circumcenter, centroid, orthocenter. So be sure you study those definitions. I'll let you read them on your own. And it turns out that this says something about an in-center is a center of a circle that's going to be inscribed inside the triangle, and it tells you how to find the in-center in this proposition. And the same thing is going to be true for circumcenter. This theorem tells you how to find it. It's going to be the center of a circle which is going to be circumscribed about the triangle. There's an inequality about medians. And then we have an Isosceles triangle theorem. Actually, part A repeats an earlier theorem, and part B, C, and D are relate to some of these things about triangle centers here. And so does Proposition 61, kind of relates to some of this earlier. One thing it says, it's regular if and only if it's equilateral, and it's regular if and only if it's equiangular. Okay. All right, so there's a quick overview of all the statements of the theorems and the definitions and the one postulate we added here. It's very important you know what these theorems, propositions say. It's not important that you know them by number. In fact, I've probably changed the numbers pretty much every week so far, because I'll go in and say, oh, I need to add another one here or there. So don't say, it's not important that you know, okay, what does Proposition 39 say? But I could say something about you should basically know what these things say, in the sense that I could come in here and give you, some of these are important enough you should be able to state them. For example, if I just say, what is the ASA triangle congruence theorem, you should be able to state it. Here's 3 different ways you could do that, but you do have to state it one of the 3 ways. So if they've got big names like that, you may need to actually just be able to say what it says. But oftentimes what I might do on the test or quiz or something, I might just say, I won't say, state this theorem. More than likely what I'll say is, maybe I might give you the theorem with some blanks in it. And you have to know the theorem well enough to fill in some of the blanks and then figure out, and state the rest of it. Definitions are definitely things that I will definitely ask you on quizzes and or tests, and I'll just say, what is the definition of a triangle? What's the definition of the interior of a triangle? Some of these have shown up on quizzes and might show up on another quiz or an exam. So again, very important that you work on memorizing definitions and familiarize yourself with the propositions as well, so that you can do some fill in the blanks there.